This is called the Mpemba Effect, named after a Tanzanian student named Erasto Mpemba who noticed it while making ice cream in 1963. His teacher told him he was wrong. He wasn't. Scientists have been arguing about WHY for over 50 years. Let me walk you through the 4 biggest theories. Theory 1, evaporation. When water is hot, molecules at the surface are moving so fast they literally escape into the air as steam. That means the hot water is losing mass. Less water to freeze means it freezes faster. Simple, right? But here's the thing. Evaporation alone doesn't account for the full effect. The math doesn't add up. Okay, so evaporation is part of the story, but not all of it. What if the answer isn't just about what leaves the water, but what was hiding inside it all along? Theory 2, dissolved gases. Cold water is full of tiny dissolved gas bubbles you can't even see. When you heat water up, those gases escape. Now watch what that does to the flow inside. Hot water creates these gorgeous convection currents, swirling cells that distribute heat evenly and cool the water faster. But cold water, it just sits there, stratified, stagnant layers trapping heat in the middle like insulation. The cold water is literally sabotaging itself. Here's where it gets really weird. What if cold water doesn't actually freeze at 0 degrees? What if it gets stuck? Theory 3, supercooling. See, water doesn't always freeze right at 0. Sometimes cold water drops below freezing and just stays liquid. It's called supercooling, a nucleation trap, where the molecules can't organize into ice crystals because there's no seed, no trigger point. The water is colder than ice but refuses to become ice. Meanwhile, hot water, because of its convection and dissolved gas loss, has more nucleation sites. It finds its trigger faster. The cold water is stuck in a thermodynamic waiting room. Those 3 theories are all real. They all contribute. But the deepest explanation? It lives at the scale of individual bonds between water molecules. And this one is beautiful. In cold water, hydrogen bonds are tight, locked in. The molecules are already holding hands in this tangled web. To freeze, they need to rearrange into the perfect hexagonal lattice of ice, but they're stuck in a local minimum. They have to break bonds just to rebuild them in the right order. Now hot water, its bonds are already broken. The molecules are free. And when they cool down, they don't have to untangle anything. They just fall into place. It's like, imagine trying to organize a room that's messy versus a room that's been completely empty. Sometimes destruction is the first step to perfect order. For decades, these were just competing hypotheses. Nobody could unify them. Then in 2020, a team of physicists cracked something open. They showed the Mpemba effect isn't just about water. It's about how any system moves through possibility space. Here's the twist that blew my mind. This same principle, heating something up to help it reach its optimal state faster. It's not just physics. Computer scientists figured this out decades ago. It's called simulated annealing. When a computer needs to find the best solution to a massive problem, like the optimal route through 1,000 cities, a greedy algorithm just takes the nearest good option and gets stuck. But simulated annealing does something counterintuitive. It heats the system up first, adds randomness, lets the search bounce around wildly, accepting bad solutions on purpose. Then it slowly cools down, and as it cools, it converges on the global optimum. The same principle as the Mpemba effect. Start hot, end optimal. The detour through chaos is the shortcut to order. The Mpemba effect isn't just a quirky fact about ice cubes. It's a deep truth about how nature finds order. Sometimes you have to break every bond to build the right ones. Sometimes the system that looks furthest from its goal is actually closest. From freezing water to optimizing algorithms to maybe even how we grow as people, sometimes the longest path through heat is the shortcut to cold. Thank you for watching. Stay curious. I'm Scientific Nipsey, and I'll catch you on the next one.